So let's may slowly look into the second one. I redraw it here as well, and I did something which is usually not correct. I moved a bit this circle for the negotiation there. So usually we are directly drawing that at the box, the not symbol, but I will change it a bit because what I will do here is introducing additional signals as well. So I will have here the signal C, and I will have here the signal D, and here D not.
Then why don't you just write C and D not directly?
Because in the table, I guess if it is easier to understand if we are doing this additional step in between.
Okay.
And then we will have here E and E naught, and our E naught will be epsilon. So you don't have to do that. If you are fine with directly filling in, then it's of course okay as well. But in the case for the explanation, I will do it much more in detail than I would usually do, in the hope that this is helping you understanding. And now we have 2 input bits. So overall, we have just 4 different bit patterns that we have to look into. So let's write them here, A, B. And AB can be 0, 0, 0, 1, 1, 0, and 1, 1. That's it. Now let's look into C. So C is 1 if both inputs are 1. So that's the case here. Okay. Then the next one that we have to analyze is D. And D is 1 if either A or B are 1. So we have 0, 1, 1, 1. And now we have, in reality, the D naught. So D naught, just opposite, so 1, 0, 0, 0. And now our E is C or D naught. So if C is 1 or D naught is 1, then our E is 1. So D naught is 1 here, and C is 1 there. And for the other cases, it is 0. And now our final output epsilon is E naught. So epsilon is 1 if E is 0, and that's the case for these 2 bit patterns. So overall, if we would write the DNF, then our epsilon would be A not B or A B not. And that's nothing else than A XOR B. So what we have there is an XOR gate.
Excuse me, sir.
Yeah.
I really don't get this one yet. Um, the final output, like this is a NOT gate. For the final output, it has one AND gate, a NOT gate interconnected. Then for the final, it's a NOT gate, right?
So you have here a NOT.
Yeah. Yeah,
That's
a
why I
NOT
defined here E, and your epsilon is E NOT.
NOT. Okay.
And
So,
therefore, so E is 1 for these two cases, which means E naught is 1 if E is 0.
okay.
It's just inverted from here to there. And the same
Okay.
from here to here.
Okay. Okay.
Sir,
So it's
isn't
not
that a NOR gate?
That's a NOR, yeah. So this one here is a NOR in combination.
okay. Sorry. For the NOR gate to produce an output of 1, both input has to be 0, right?
Right?
Okay, so that means the output for the AND gate and the first NOR gate has to be 0, right?
Sorry, again.
Yeah, like the output for the first two gates there, the AND gate and the NOR gate there, the first ones, like their output has to be 0 for the final output to be 1, right?
Yes, and that's the case. So the output of the first one is C. Sorry. That's the output of the first one. And that output of the second one is D naught. And it's 0 here and here. And that's where we have the two ones. So
Okay, okay, I
the
understand now.
input of the NOR gate are C and D naught.
Okay, I get it now. Thank you.
You're welcome. Further questions on that example? Okay, then let's come to the next one. Third, so derive and simplify the disjunctive normal form. So first of all, draw the schematics of the non-simplified disjunctive normal form and of the simplified form. And then create a Carnot map from the table. And does it work with an odd number of variables? We already did. And derive the simplest algebraic expression which delivers the result. So again, you're trying that by your own, and we are solving that after the break at 11:30, I would recommend. So then you can start on working on that, and over the break you can continue. And then we are looking into. So the first thing you have to do is derive the disjunctive normal form, simplify the disjunctive normal form, and then do the same simplification using the K-map, and the result should be, of course, the same.
Sure, you are muted. Sir, you are muted.
Excuse me, Professor, you're on mute. Excuse me, sir, you're on mute. Can't hear you.
Professor, excuse me, you are muted.
Hello, Professor. Hello, you are muted, please.
Hello, sir. Hello, sir. You're on mute, please. We can't hear you.
Are you hearing me now?
Yes.
Crazy. So
Yes,
in
now
the
we hear you.
video, I was not muted. It seems like the microphone was not working. Then let's just repeat. So I developed here, or I just wrote here the disjunctive normal form by connecting all lines where the output is 1 with an OR. So the first one is A naught, B naught, C naught. Then we have A, B naught, C naught, A, B naught, C, A, B, C naught, and A, B, C. And I wrote that, so I have here 1, 2, 3, 4, 5 terms who have an AND, and they are connected to each other with an OR. So here we have the 5 AND gates and the OR gate where all the AND gates are going into. On the first one, I have A naught, B naught, C naught, A, B naught, C naught, A, B naught, C, A, B, C naught, and A, B, C. So that one here is the logic circuit for the non-simplified form. Okay? And now we are simplifying the equation here. And we are doing that in building pairs where only one input is different and two are staying the same. So, for example, we have here in the second term A, B naught, C naught, and here we have A, B naught, C. So we can write that one as A, B naught, C or C naught. Here we have A, B, C naught and A, B, C. So we can write here A, B, C naught or C. And the remaining is the A naught, B naught, C naught. So only one bit is changing. Theoretically, you can also combine these two, for example, to B naught, C naught, A or A naught. And now we can further simplify that. So what we have here now is A naught, B naught, C naught, or A, B naught, or A, B. And now we can combine these two together. And you are getting here A naught, B naught, C naught, or A, choose the correct color, A, B naught or B, which is just A. So it is A naught, B naught, C naught, or A. So that's with directly simplifying. And if you are now drawing that one, it would look like A, B, C not. And the output of that is the input of our OR. Or the second input that we have here is just A. So that's the same logic circuit. And now you see the advantage there. If you are programming that, you can have either that part as code or that one. And of course, the processor load for that one is much smaller than if you're having this combination here. And now the last thing is to simplify that with the K-map as well. we have 3 inputs for the K-map, A, B, C. So let's have here A and B, C, but doesn't really matter how you're arranging. The important thing is to write here as a gray code. So 0, 0, 0, 1, 1, 1, 1, 0. And here we just have 0 and 1. And again, let me just add, that's nothing else than B naught, C naught, B naught, C, B, C, and B, C naught, and A naught, A. And now we are filling in from the truth table. So it is 1 for A, B, C. So that's here. A. Sorry, A. Yeah, that was the last one. So A, B, C. It is 1 for A naught, B naught, C naught. So that's here. A naught, B naught, C naught. Then it is 1 for A, B naught, C naught. That's that one. For A, B naught, C. And for A, B, C naught. And now we are combining here, and you remember you always have to combine 2 to the power of n elements, so 1, 2, 4, 8, and so on. So we are combining here this 4. And if you are looking into that, that's nothing else than A. So the green frame is true if A is true, independent from B and C. So B and C can be 0, 0, 0, 1, 1, 0, 1, 1. So that's A. Or here. And here we have A naught, B naught, C naught. And if you now compare the two forms, we have A or A naught, B naught, C naught, independent if you are using the K-map to simplify or if you are simplifying the DNF. Questions on that?
Sir, can you explain again how did you write the DNF statement?
Yes, of course. So what I did was nothing else than just writing here the combinations of the inputs for each case where our epsilon is 1. So it is 1 here, A naught, B naught, C naught. Then the second one is there, A, B naught, C naught. The next one is here, A, B naught, C. Then, let's pick another color, here, A, B, C naught. And the very last one, here, A, B, C. And
When
I'm
you
just
simplify it
connecting
further,
all of them with an OR. And then I'm just simplifying. Or do you have questions to the simplification as well?
you said you're collecting with OR?
Yes, the plus is an or. So here we have a dot in between, that's an and. If you want to have that in addition. And all the terms are connected with each other with an or. Cause you see, it is one if A naught and B naught and C naught, or A, B naught, C naught, or A, B naught, C, or A, B, C naught, or A, B, C. Do you need further explanation for that, or is it fine?
One second, sir. I'm processing it.
You're trying once again by your own, or?
Yeah, that's what I'm doing.
Okay. And then for simplifying, what I'm doing is I'm searching for terms which are differing in only one input variable. And the others are staying the same. So like here, A, B naught, C naught, or A, B naught, C, because then I can apply here the distributive property and say that's A and B naught and C or C naught. And C or C naught
Sir,
is always one. Yeah.
the C plus C naught, where did you write that in the second line?
Yeah.
Yeah, this one, the C plus C naught.
Yeah. What is C or C naught? That's always one.
Like in the second line, you have not written C plus C naught.
Where is it? You mean that one? Is that the second line? Or what do you mean by the second line?
On second line of the fourth line, let's say, fourth line.
That one here.
Yeah, here you have not written
Yeah,
C plus C
because
naught.
C or C naught is always one. So if you have a logic gate, just imagine with an OR, the output you have epsilon, and at the input you have C or C naught. The output is always one. So if C is 0, then that path is true. If C is 1, then that path is true. It's always 1. And if you are looking back and studying the material, then you are seeing here that X or X prime, so X or X naught is always 1. Why are you not seeing? One second. So my screen mirroring stopped working, but let's hope it is fixing. So, let's see. So that's the complement element. And you always have an x or x naught is equal to 1. And that's what we have here. C or C naught is always 1. Clear?
Sir, your screen is not visible for me.
The screen is not visible. Why not? Now?
Yes.
Okay. So here we have the complement element, x or x prime. So x or x naught is always 1, and x and x naught is always 0. And that's what we have here. We have here C or C naught, and that's always 1. And therefore, I'm just skipping the 1, because it makes no difference if I have an additional input at the AND gate, which is always 1. Because A and 1 is A.
Yes, sir, I got that now.
Okay,
Thank you.
you're welcome.
Hello, sir. I have
Yes.
question on the key map
Uh-huh.
because if I change the setting, I put AB and I put C down. My answer is the same, but I don't know. I feel the same. If you can go about that one too slowly, please.
Of course. So let me just copy that. Let me just add a page. So you have A and B here
Yes,
and C there.
yes.
Okay. Then let me just fill in. So we have A, B, C. If all of them are 0, you have a 1 here. Then you have a 1 A, B naught, C naught, A here. A, B naught, C there. A, B, C naught. And here, right? That's how your map is looking like, right?
Yes, yes, yes.
Okay. So what you can combine here as well are these 4. Okay.
Um,
And that's simply A. So you see, it is 1 if A is 1, independent from B. And again, it is 1 if A is 1, independent from C. So that's the independency from C. That's the independency from B.
okay.
So the orange one is A. And you have here that one in addition. And that's A naught, B naught, C naught.
Okay, thank you.
You're welcome. So then let's come to the next example. We talked last week about an additional problem, which is not in the slides described, about this 2 out of 3 setting. Let me just see if I can find it briefly. Here. So we said 3 smoke detectors per room. If 2 or more are detecting smoke, then we will have an alarm. And what you had to do there is, or what you have to do there is simplifying that one also from the DNF and with KMap. So what do I have for KMap? When did I get an alarm? So I'm getting an alarm here for each the light blue outputs. So S1, S2, and S3 not, or S1, S2 not, S3, or S1 not, S2, S3, or S1, S2, S3. And you see now, the terms are always changing in two variables, with exception of the last one. So I can combine the last one either with this, or with that. But now I will add there something, which is not changing anything. I will add here an S1, S2, S3 twice. So if we would draw the circuit, let's maybe do that. S1, S2, S3. Then I have here, for the moment, 4 AND gates. I have S1, S2, S3 not. Then I have S1, S2 not, S3. Then I have S1 not, S2, S3. And S1, S2, S3. And they are all moving into one OR. And that's our alarm. What I'm now doing in the KNF is nothing else than adding that two more times. So I just added these two gray paths. And if now that path will be true, because S1, S2, and S3 are true, then they will be true as well. But as I have an OR, that doesn't change anything. Clear? Why this is not changing anything if I'm just repeating and adding an existing element which is connected with an OR to that. Because I'm just creating another one at the OR input, but it is already one, therefore it is not changing. So, and now I have one element for each to simplify. So I can simplify the two green ones. And they will become S1, S2, and S3 or S3 not, which is S1, S2, or that one, color and that one. So that's S1, S3, S2 or S2 not, or the last set that is over. What did I write here? That should be S1, S2. So S1 not or S2 or S3. So the red one is then S2 and S3 and S1 or S1 not. And I can skip each time those parts in the brackets. And I'm ending up here in S1 and S2 or S1 and S3 or S2 and S3. So if two of the sensors are 1, then the output will be 1. And if 3 of the sensors are 1, then all 3 of these requirements will be fulfilled. So the next one, the S1 and S2 and S3, is already fulfilled by that, or by that, or by that. Of course, and so it is fulfilled by that, that, and that. If you are simplifying that with the K-map, having here S1, S2, and here S3, 0, 0, 0, 1, 1, 1, 1, 0, 0, and 1, then it is true if S1, S2 are 1 and S3 is 0. If S1 and S3 are 1 and S2 is 0, so here, if S3 and S2 and S1 is 0, and if all of them are 1. And now I'm combining them in the same manner. So S1, S2. Let me enlarge a bit. So here I have S S1, S2, independent from S3. Or and S1, S3. Orange one. S1, S3, independent from S2. Is that one here? So the orange one, we have S1, S3, and S2 is 0 or 1. Or the last one, the red one, S2, S3, independent from S1. So here we have S2, S3, and S1 can be 0 or 1. So exactly the same output like we had before, which is leading us now to redraw that as the following. Again. S1, S2, S3. And we have 3 ends. Sorry. So the first one we have S1, S2. And just no S3. For the second one, we have S1, S3. And just no S2. And for the last one, we have S2, S3. And they are feeding into an OR, which is our alarm. And that's not a simplified one. So here we have the DNF, and here we had the simplified one. Independent if you are simplifying DNF or if you are using the K-map to simplify. Questions on that example?
So I don't understand what's the purpose of the last two logic gates that you have drawn in the DNF.
I brought them because I added here twice the last term. So I have here or S1, S2, S3. And I added them a second or a third time. And here I just wanted to show you if I'm adding them. So I added them here in gray, and I also added them here in gray. If I'm adding them, that does not make a difference. Because if that path is true, then this path will be true, and this path will be true as well. If that path is false, then that one will be false as well. So it is not changing my overall behavior of my logic gate if I'm adding that, the same circuit a second and a third time. But for simplifying, I need it because I have here a term that I can simplify with this S1, S2, S3, because here the S3 is changing. But then if I would not have the last ones, I cannot simplify those two, because from here to here, there are two terms changing, S1 and S2. therefore, I'm adding this S1, S2, S3 again and the second time again to use them to simplify the second and the third term. So I'm extending the DNF to simplify. I'm not just simplifying. Before I'm simplifying, I'm even extending to be able to simplify. Clear?
So that means just to simplify, we can also add the other like logic gates as well.
If you are not changing the overall logic, then of course. So, I mean, if you are just for simplifying, adding here or S1, that would be, of course, not true. Because then you would change your truth table. Because then you would get a 1 here, sorry, here in addition. Because then it would only depend on S1. So if you're adding something, you have to add something which is not changing the truth table. And I added here something which is not changing the truth table because it is already there. Clear?
Yes, sir.
Okay. Any other questions on that before we are going to the next problem?
So I just don't understand, like, in exam, if something like this comes, I don't understand if we have to draw an extra circuit to simplify or not. That's the bit I'm not understanding.
It depends on if it is requested to do that or not.
Okay, so they will mention that.
Yeah.
Okay.
So if like in this previous example, it was like that. So here the question was draw the schematic of the non-simplified disjunctive normal form and of the simplified form. So you have to write down the DNF. You have to simplify the DNF. You have to draw both. And then you have to use the K-map approach to simplify the truth table. And that has to be the same result. Otherwise, there is something wrong. So that's what we did here. We noted the DNF. We simplified the DNF. We draw the general DNF. We draw the simplified DNF. And we have proven with the K-map that our simplification of the DNF was correct.
Sir. Sir, this working, I'm not seeing the working in Ireland. Is it because you do not post them or what?
What are you not seeing in Islander?
The working that you do in class.
Right, so you are supposed to take notes by your own, depending on what is necessary for you to note. I mean, I don't know, maybe you don't have to take any notes because you can just keep that. So what shall I post? For the tutorials and for the problems and for the notations I'm doing, you have to cite by your own if this is important for you or if you can keep that without noting.
Yes,
That's
sir.
why
I
we
do
are
note
doing
that
them.
by myself, but sometimes like I need to cross-reference with the answers that you do in class.
But therefore, I'm asking during the tutorials if you have any further questions.
Okay, okay.
And again, I don't want to upload the notes because I just don't want. I trying to kind of force you to take notes by your own because if you're noting the things by your own, then you are learning. If you have to learn math, then you are learning if you are calculating. You are not learning by reading a book. And that's the same here. You are not learning by reading through my notes. You are learning if you're doing that by your own. That's the reason why I'm kind of forcing you to take the notes by your own. Because that's the easiest to learn, I guess. Lucas, you have a question. Go ahead.
Sir, can you recommend a book that has exercises for us to solve?
So this book that the lecture is relying on, this Glenn Brooks, let me just open it.
You mean the computer science and overview?
Yes, this Brookshire, there are two.
There are not so many exercises there of logic gates. There are just a few.
Yeah, therefore we are doing additional ones in the tutorial, and for sure you're finding tons of that online as well, of the Boolean examples. So you want to have more exercises of that? Am I understanding correctly?
Yeah, just maybe a book with answers to check it.
Okay. Let me look into if I'm finding something else. Just 1 second. There is a second one mentioned. It's a German one, but I mean the logic behind that is independent from the logic. A one is a one in English, in Russian, and in German. Doesn't really matter if there is something more on that.
Maybe in Chinese it's not.
Maybe. But I'm not able to read that, therefore I will not recommend a Chinese book, don't worry.
But maybe even if you are able to read it, it's not.
Even when yes. There is also not too much. So what I can recommend as well is what we already did several times in the lecture with this logically or with any other simulator. Because overall, if you want, let me just share the screen differently. So if you are taking here an example with 3 inputs and 1 output, and you are combining them, I don't know, howsoever, so however you want, doesn't really matter. Like that if you want. Then you can try to do that. So you can try to note here the different input states, the output, and you can easily check. I have no any idea yet there is a case. So if the first one is on, and that seems to be the only. So what I have created here is nothing else than an epsilon is equal to A. But you can try that. So here you can easily test if you can simplify these 3 input states with this connection to epsilon is equal to A. For truth table. Or with a K-map or whatever. And you can check yourself.
Okay, thank you.
You're welcome. Okay, then let's come to the next problem within that group here. that one here. So what is the Boolean expression for that circuit? So let's start with problem A here. Again, write down the truth table out of that, or try to write down the expression directly and simplify if possible. So maybe you're trying that by your own till half. So for 7 minutes, it's not too complicated. And then we are looking into that together. So let's look into the expression here. At the first one is, or at the upper part, A not and B. At the lower part, we have A or B not, and they are connected with an AND to each other. So maybe again, that AND is that one. That AND is that one here. And the OR is that one. Okay. Now we can write that as A not and A and B, or B and B not. So I just brought the B into the brackets. And I will now do the same with A. So that's A not A B, or A not B B not. And now that one here is 0 and that one is 0. So B and B not is 0. So what I have here is 0. There is no any combination where my output is getting 1 for that circuit. So what you can do if you want to prove that with a truth table is adding here two signals, C and D, and then writing here the possible combinations for A and B. 0, 0, 0, 1, 1, 0, 1, 1. C is A not B. So here. D is A or B not. Sorry. So that's D and that's C. So A or B not. A, B not. And now, finally, our output is C and D. And that's a reverse 0. And even if you want to check, you can do that easily if you our algebraic tool. Where I am. So here I have A not and B, and